Welcome to today's paper reading. Today's paper is titled, A Survey on Hallucination in Large Vision Language Models. This paper was published on the AR14 preprint by Hanchao Liu and colleagues from Huawei Technologies. In this survey, the focus is on the phenomenon of hallucinations in large vision language models, LVLMs. Hallucinations are defined as the misalignment between factual visual content and the corresponding textual generation, which presents a significant challenge for these models. The survey begins by clarifying the concept of hallucinations, highlighting various symptoms and the unique challenges they pose. It then outlines benchmarks and methodologies specifically designed to evaluate these hallucinations. Additionally, the survey investigates the root causes of these hallucinations, drawing insights from both the training data and the model components. The survey also critically reviews existing methods for mitigating hallucinations and discusses open questions and future directions in this area. To support ongoing research, a repository of relevant references is maintained for continuous updates. In the field of artificial intelligence, large vision language models, LVLMs, have been developed to integrate visual and textual features, enhancing natural language understanding and generation. Models like MiniGPT-4, LVA, and LVA 1.5 exemplify this integration. However, an issue impeding their practical application is hallucination, where there is a disagreement between the factual content of images and the generated textual content. Hallucination can manifest as errors in object, attribute, and relation descriptions, and it is multifaceted, affecting both cognitive judgments and visual semantics. This study focuses on analyzing the causes of hallucinations in LVLMs, which include the generative nature of large language models, biased training data, and misalignments among different modalities. Mitigation methods currently focus on optimizing training data and refining model modules to reduce hallucination occurrences. The research aims to provide insights for future development of more reliable and efficient LVLMs. Figure 1 illustrates examples of hallucinations in large vision language models, LVLMs. These hallucinations can appear as deficiencies in various vision language tasks, such as judgment and description, or as factual errors in different visual semantics, including objects, attributes, and relations. For instance, the model might incorrectly affirm the presence of a cat in an image where there is none, or inaccurately describe the attributes of objects in the image. These examples highlight the multifaceted nature of hallucinations in LVLMs, which can occur across various semantic dimensions. The architecture of large vision language models, LVLMs, typically includes a visual encoder, a modality connection module, and a large language model, LLM. The visual encoder transforms images into visual tokens, while the connection module aligns these tokens with the LLM's word embedding space. The LLM then synthesizes this information to produce responses. Hallucination in LVLMs refers to discrepancies between visual input and textual output, which can manifest as judgment hallucinations, where the model's response contradicts the visual data, or description hallucinations, where the model fails to accurately depict visual information. Challenges in mitigating hallucinations include the difficulty in detecting them due to the multimodal nature of LVLMs, the multifaceted causes such as visual uncertainty and data-related issues, and the resource-intensive methods required for effective mitigation. In evaluating large vision language models, LVLMs, for hallucination, two primary approaches are used: assessing non-hallucinatory content generation and evaluating hallucination discrimination. For non-hallucinatory generation, methods include handcrafted pipelines like chair and model-based end-to-end approaches such as LLM-based evaluation. Hallucination discrimination methods typically use a question-answering format to assess the model's ability to correctly identify hallucinations. Benchmarks for these evaluations are categorized into discriminative and generative types, with some, like AMBER, integrating both approaches. These benchmarks help in understanding and mitigating hallucinations in LVLMs. Table 1 categorizes hallucination evaluation benchmarks for LVLMs into discriminative, DIS, and generative, GEN types. It highlights benchmarks like POPE, NOPE, and CIM for discriminative evaluations, focusing on object hallucinations and using accuracy metrics. Generative benchmarks, such as mHal-detect and Yifei, extend to attribute and relation hallucinations, employing more varied metrics like reward model score and FAITH score. Amber integrates both types of tasks, showcasing a comprehensive approach to LVLM evaluation. Figure 2 categorizes the evaluation methods for large vision language models, LVLMs, into three main types: handcrafted pipeline methods, model-based end-to-end methods, and evaluation on hallucination discrimination. Handcrafted pipeline methods include Chair, CCVAL, and FAITH-SCORE, which are designed to measure the proportion of hallucinated content in outputs. Model-based end-to-end methods are further divided into LLM-based evaluation and hallucination data-driven model evaluation, with examples like Yifei and mHal-detect. Lastly, evaluation on hallucination discrimination includes methods such as POPE, CIM, and NOPE, which assess the ability of LVLMs to discriminate between hallucinated and non-hallucinated content. The causes of hallucinations in large vision language models, LVLMs, can be categorized into three main aspects. Firstly, data-related issues such as data bias, annotation irrelevance, and homogeneity in training data can lead to hallucinations. Data bias includes imbalanced question-answer pairs, where models tend to favor certain answers. Annotation irrelevance refers to mismatched instructions generated by models, which do not accurately correspond to image content. Homogeneity in data limits the model's ability to understand diverse visual information. Secondly, limitations in vision encoders, such as limited visual resolution and fine-grained visual semantics, contribute to hallucinations. Vision encoders often use smaller image resolutions, which can affect object recognition accuracy. Contrastive learning, while effective, focuses mainly on salient objects, missing finer details. Lastly, issues in modality alignment, including the simplicity of connection modules and limited token constraints, can cause misalignment between visual and textual features, leading to hallucinations. Simple connection modules, like linear layers, may not fully integrate multimodal data. Limited token constraints, where a fixed number of tokens are used, can result in information loss during alignment. Figure 3 illustrates the various causes of hallucinations in large vision language models, LVLMs, and the corresponding mitigation strategies. The causes are categorized into data-related issues, such as data bias and annotation irrelevance, which lead to models providing consistent but incorrect answers. Vision encoder limitations, including limited visual resolution and fine-grained visual semantics, also contribute to hallucinations. Additionally, issues in modality alignment, such as the simplicity of connection modules and limited token constraints, exacerbate the problem. The figure outlines specific mitigation methods tailored to each cause, aiming to enhance the quality and reliability of LVLM outputs. The mitigation of hallucinations in large vision language models, LVLMs, involves several key strategies. Firstly, in data mitigation, methods like CIM, LRV instruction, and ferret address bias and enrich annotations with datasets such as mHal-detect and GRIT. Fine-grained instruction samples covering multi-round conversations are also generated. Secondly, enhancing the vision encoder includes scaling up image resolution and improving perceptual capabilities with models like vCoder and Monkey. Lastly, the connection module is enhanced through better alignment training and more capable modules like LVLM 1.5 and QLMA, which improve modality alignment and reduce hallucination risks. The research on large vision language models, LVLMs, is still in its early stages, offering significant potential for development and improvement. One key area for future research is the refinement of supervision objectives. Current LVLMs primarily use coarse-grained alignments and whole-image instruction tuning, which limits their ability to understand complex visual details. More detailed, spatially aware supervision methods, such as object-masked language modeling and position-enhanced instruction following, hold great promise for advancing these models. Another direction is the enrichment of modalities. Integrating multimodal signals not only expands the capabilities of models but also enhances their performance on single-modal tasks. High-quality representation learning from correlated and complementary information is a key benefit. Recent research has made strides in incorporating additional modalities, such as videos, through methods like cache retrieval and pre-alignment. Designing advanced paradigms for coupling multiple modalities is a worthwhile avenue for further investigation. Additionally, treating LVLMs as agents empowered by large language models, LLMs, can significantly enhance their understanding and reasoning capabilities. Teaching LVLMs to utilize visual tools and reason with accurate and structured outputs, rather than relying on more advanced visual encoders, is a practical and promising approach. Recent research in this area has demonstrated impressive fidelity in tasks like OCR-VQA, object tagging, and grounding. In this survey, the authors explore the capabilities of large vision language models, LVLMs, which are equipped with advanced vision encoders, robust large language models, LLMs, and modality connection modules. These models excel in open-domain vision language tasks. However, the practical application of LVLMs is significantly challenged by hallucinations. The authors conduct a meticulous investigation into this phenomenon, introducing innovative evaluation methods and pertinent benchmarks. They provide a detailed analysis of the fundamental causes behind these hallucinations and discuss effective mitigation approaches. Additionally, the authors delve into existing challenges and potential future directions. This survey aims to lay a foundation for tackling the complexities of hallucinations in LVLMs and to facilitate future research towards the practical implementation of these models in various applications. Thank you for watching.